We had a session talking about reliability impacts on the systems with high IBRs, and we kind of alluded to talking into what our system needs for new tools and old tools that may be used in a new way. And so today we have the entire session about EMT tools and EMT practices and applications. So you'll hear from two system operators. First, kind of similar to the session we had yesterday, and then kind of more broad perspective on EMT studies, and then also an update on NERC EMT task force and what is happening there. So without any further ado, let's go ahead and get started. And first presentation is on EMT practices at ONS, that is Brazilian system operator. And Bruno Pestana Rosa is electrical studies engineer in planning department at ONS, and all the way from Brazil. Go ahead, Bruno.
Good afternoon, guys. So my name is Bruno. I'm here to talk a little about EMT practices in ONS and how ONS is working to improve the use and the validation of EMT models to improve power system operator. So a brief summary of the presentation. I'm going to talk a little about what ONS is and the Brazilian interconnected power system, or the BIPs, as we call it. A little about EMT models in ONS today. So what are they being used nowadays? Then I'll talk very briefly about August 15th, 2023. There was a partial blackout that happened in Brazil, and it really turned around the way that we saw EMT. And it was a critical turning point to understand the future of EMT models in ONS today and what we are thinking for the future. So starting about ONS. So ONS is the system operator of the Brazilian interconnected power system. Some quick numbers. We operate over 225 gigawatt of installed capacity, over 1,500 power plants. More than 180,000 kilometers of transmission lines. And in terms of loads, we've had an average load of 75 gigawatts in 2023 and a peak demand of a little over 100 gigawatts this year. So a little about the BIPs. This is a simplified one-line diagram of our system. So it is huge. It's one of the world's largest synchronous networks. It has only one operator, that is ONS. Some quick main characteristics. We have the main load center in the south and southeastern Brazil. We have some large hydropower plants far from load centers at the north that are connected through HVDC links and through the AC interconnection. And I think this is the most important bullet from the slide. Very, very rapid increase of wind and solar generation at the northeast. And that's been a really big challenge for us, as we're going to see further ahead in the presentation. So quickly, for the BIP's electricity mix, let's focus here on the last few years. So we can see a very fast increase in both wind and more recently in solar generation. We have a huge hydroelectric potential that's different from most countries in the world, I guess. And just last year, 2023, hydro has had a participation in our mix of almost 70%. And that, together with wind and solar, allowed us to have somewhere around 90% renewables. And if we look at IBR penetration, the numbers seem low, just 20% IBR penetration when we talk in average terms for the whole system. But I was going to see a little ahead. It's all very concentrated in the Northeast region. So when we see this penetration regionalized, the situation changes a little. Okay, now talking a little about EMT models in ONS today. So basically, we use EMT models for two studies on a regular basis, multi-feed performance and transformer energization. And then we have some other ad hoc studies that are done on demand. So for multi-feed performance, We have a multi-feed configuration with a little over 20 gigawatt capacity. HVDC LCC links, they're in close electrical proximity. They all converge towards the southeast region of Brazil, where it's our main load center. And we know that this setup can lead to simultaneous commutation failures across different HVDC links, which naturally pose a risk to system stability, especially during faults or disturbances near the inverter station. So nowadays we use PSCAD with detailed EMT models of these HVDC systems to analyze this multi-feed phenomena and to simulate the interaction between the converters and the AC network to determine the commutation failure times. Then we take these commutation failure times and we use them in our RMS simulations to study system performance. So basically, there's a work in PSCAD where we have actually quite big system equivalent. It's most of our main interconnections are modeled, and we go anywhere from the 4th up to the 5th or 6th neighborhood from the converter stations. So with that system, we study commutation failure times for main contingencies, and then we take them for the RMS studies. And we are actually developing right now a software for hybrid simulation, RMS EMT. Maybe we can talk a little about it in the questions. I didn't have time to include in the presentation. But it's called NHVDC, and it's supposed to help us in this process for multi-feed performance studies. Next one will be transformer energization. Here we use ATP and a lot smaller network model up to the 2nd neighborhood. We do normal operations, simple outages, and the simulations are basically 200 random energizations with a statistical breaker. First, without pre-insertion resistors and point wave switching. If they are present, we also do simulations considering their functionality. And then the most severe conditions that are identified statistically are reproduced deterministically. Okay. So basically, these two are the regular studies. So we use PSCAD for the performance study, and then ATP for equipment withstand capability study that would be transformer energization. And then we have some other studies that are done on demand, like load rejection, single pole and triple pole auto reclosing, mostly single pole for EMT studies, transmission line energization, transient recovery voltage, and SVC hunting studies are some examples of some other studies that we do. Okay. Now going to the August 15th, 2023. So let's go over a little what happened, why it happened, and the lessons that we learned for this event. So quick event overview. In this map, we have the main interconnection power flows right before the event took place. So let's focus here on the northeast region, okay? It was exporting around 12 gigawatts of transmission with 90% IBR internal generation. So remember when I said before, we've had 20% average IBR penetration in Brazil in 2023, but it's really concentrated in the Northeast. And at the time of this event, this region had a 90% IBR internal generation. And this event started with the outage of this transmission line, Fortaleza do Xadá, which was transmitting 2 gigawatts, and it's located at the north part of the northern region. Okay. Yeah, that's useful. It's located right around here. Okay. And the system's planned and its operator, so as a single outage shouldn't have any damage whatsoever. But the RMS simulation showed that the system was stable for this outage, with all voltages within normal range of operation. What happened though was a voltage collapse across most of the Northeast region that led to cascading outages, culminating in a partial blackout that affected the North and the Northeast region mostly. So what explains this difference between why did the simulations show that the voltages across the system were controlled, but in reality, there was a voltage collapse. So for a lot of effort, a lot of investigation, and the digital fault recorder files, we identified that the main issue was with IBR performance. So the simulation showed a very fast, very optimistic response, while the equipment in the field, well, didn't. So we have some examples here. So this is from a solar power plant. We can see in blue the simulation response of this power plant. So we have a very fast response, very optimistic, very aggressive, with a lot of reactive power injection in the grid. While the system disturbance file, what really happened was a very timid response from this specific solar plant. And this was not isolated. Here we have an example of a wind power plant. Same thing we have in the simulation in blue, very fast response, contributing a lot to reactive power support, while the system disturbance file shows that it really didn't contribute at all for the disturbance. And this was seen across pretty much all IBRs in that region. So we believe that explains why we couldn't see the voltage collapse in our simulations. So naturally, after this event and these conclusions, something had to be done about our models. So this event and the lessons learned are really shaping the future of EMT and ONS. So let's talk a little about that now. Of course, we had new model requirements. So before August 15th, RMS models were provided by the plant owner. They were only validated during the commissioning phase against field tests. So this is a very simplified how the integration process works in Brazil. First, we have viability analysis, several months to a few years before integration. We use typical model, and we are interested to see if the system can take that active power injection. That's basically it. Then the pre-operational studies, that happens around 8 months before the plant integration. And here's where we use to ask for RMS models of the real equipment, no typical models. But these models were only validated in plant commissioning. That's the last step, right before integration against field tests. And we know that there are several limitations with field tests to test complex functionalities, for example, logic for reactive current injection during faults. So what we did to address this limitation, it will now be necessary to provide during the pre-operational study a PSCAD model of the real equipment accompanied by a validation report based either on laboratory tests or Hill simulations. And then the real equipment RMS model will be validated against the PSCAD. And now, since we are doing all these validations during the pre-operational studies phase, using as a benchmark the Hill simulations most often. Now during commission, we will only do fine tuning of parameters with confirmation of performance against field tests. So hopefully we believe this approach would ensure that most system behaviors are accurately modeled and validated before commissioning to reduce risks and uncertainties during the actual implementation phase, and to ensure that our RMS models that are used in our simulations are representative, because we really need to get our trust in our models back, because we lost that on the August 15th event. So that's it for new model requirements. So I talked about requiring EMT validation. How do we do that right now? So we do not have a defined routine for validating EMT models. This was intentional. We wanted to allow manufacturers to have a flexibility to use the validation processes that they already had, maybe to comply with other system operators in different countries. So we do, however, although it's really flexible, we do not have a defined routine. We have some minimal requirements. So it must be the manufacturer's official three-phase EMT model for studies. It can be a typical model. All protection, control, and measurement logic must be represented. So sampling rates, communication delays, measurement sampling, they're inherent to the equipment. Those are very important for us. The validation should include fault conditions under and over voltages, and be representative of various operational conditions. So we want tests in different SCR levels with different active power generation, etc. And the validation must have been performed on equipment that is identical or equivalent to that implemented in the field, because some manufacturers have several models of inverters, for example, integrated in our system. And of course, while in this first step, we don't have a formal guide for this validation, we are engaging with manufacturers to better understand the specific details of each model. So once this initial phase is complete, we will work toward establishing formal guidelines for this validation process. So we are learning as we go. And this phase approach would ensure that the validation that we eventually implement will be robust and will be aligned with industry practices, while we also ensure that we have a rapid initial submission of validated EMT models, because we really need that as fast as possible to establish the representativeness of our RMS models. So that's basically it for EMT validation. So we are requesting a lot of new models. And what are our objectives with these models? What do we intend to get from them? So first, short-term objective would be a benchmark for RMS model validation. That's what we want right now. So we need to complete the validation of PSCAD and RMS models based on laboratory and or Hill tests to ensure consistency between these different levels of modeling. That's our short-term objective. And as I said, for the EMT validation, we don't yet have formal guidelines, but for the EMT versus RMS validation, the validation of the RMS model, there is a very specific guide with requirements regarding simulation time window, sampling rate, format, and grid structure. There's a list of variables to collect and a very comprehensive test scenarios with voltage and power steps, frequency excursions, shunt switching, faults, oscillation events, LVRT, HVRT tests, and so on. So for this specific validation of the RMS models, there is a very detailed guide. Okay. And then we go to the long-term objectives. So one of them would be to use these PSCAD models to improve evaluation of oscillation events in IBR controllers. So now this assessment is based purely on PMU data and the support from the equipment manufacturer. So we can pretty much only use the PMUs that we have to pinpoint the location and to pinpoint the generator that is originating the forced oscillation. And then we depend totally on the manufacturer to do the analysis of what's happening in that plant. So we hope that the integration of these detailed models into ONS's framework of studies would allow for some more independent, more thorough analysis of the IBR controller performance. And if I may say, these oscillations are becoming more and more common in our system nowadays with the massive integration of these IBR sources, especially when we look at the Northeast region and more recently, even at the Southeast region and a very specific part of it, the north of the state of Minas Gerais, that's having a lot of integration of solar power sources. So that's the first one. The second, and I think that could be even the most important objective for us, would be new studies focused on high IBR penetration and low SCR areas. So we want to leverage these models to do some advanced studies in areas with high penetration of IBRs or low SCR ratios, and because we know these regions are particularly susceptible to stability issues, such as voltage and frequency oscillations. And we hope that with this database of EMT models in place, ONS can conduct focused studies that explore new mitigation strategies, enhance system planning, and ensure a more robust integration of IBRs. So we want to have this ability to simulate complex scenarios, complex interactions, and get valuable insights for system behavior. So this graph here on the side, I'm not sure if you guys can see the numbers, but it's really interesting because it takes the average IBR penetration and it regionalizes it by state. So as I said in the beginning of the presentation, in 2023, we had an average IBR penetration in the whole of Brazil of around 20%. If we look at the Northeast region, that's this region right here, where we see the stronger colors, that's an average of around 70%. So from 20, we got to 70% IBR penetration. And if we go even more regionalized in the northern part of the region, we have these 4 states here. One of them with a penetration of 85% is the more light colored one, and the other 3 with a penetration higher than 95%. And that's average numbers. That's what we see the whole year in the States. If we took instantaneous penetration, we'd get things like 100%, very close to 100% IBR penetration in the Northeast region. The record for the whole of the system was a little above 50%. But what I mean is we are not really sure if we even have the resources today to accurately study this region. So we're hoping that this EMT database can help us get some insights and see if we are really accurately representing all the dynamics that exist in this very specific part of our system. And coincidentally or not, the transmission line that tripped and originated the whole August 15th event, it's right here. So it's right in the middle of this really dark colored, very high penetration IBR states. So that's our long-term objective. And that's actually basically what I had to present for you guys today. So as you could see, after the August 15th event, a lot of things are changing in ONS. We are really diving deep into IBRs. We have a lot of projects internally to study things like screening methods and softwares. We have a lot of external projects along with GPST, along with EPRI, to study modeling, to study validation, integration process requirements. So we learned a lot from the event, and we are still learning. A lot of challenges ahead, but I think we're on the right path. So thank you for your attention.
Thank you, Bruno. Very fascinating progress just within slightly over a year, from RMS simulations all the way to EMT and modeling and all that. And so next one is Brad Marszalkowski from ISO New England. He's a supervisor of resource integration, and he'll be talking about EMT practices here in ISO New England.
Hi, everyone. As Shirley said, I'm Brad Marszalkowski. I work at ISO New England as the supervisor of resource integration. And today, talking a bit about the EMT practices and methodologies here for the region. So we'll start with kind of when does ISO do an EMT study? What that EMT study kind of looks like, the requirements around the models, and then some future work that's going to be coming down the pipeline as well. So ISO New England started doing EMT studies probably about 11 or 12 years ago. There was an SVC that was going up in the northern part of Maine, which was causing some instantaneous overvoltage issues on some of the wind farms that we have up there. In northern Maine, there's a lot of different wind farms up there. And so as part of the integration of that SVC, they started looking at the transients and found that they needed to parameterize the controls specific for that SVC for those sort of wind farms. And so that kind of spawned the original requirement because moving forward, any wind farm that was going up in that northern part of Maine needed an EMT study to make sure that they didn't have any sort of control interactions with the SVC. And so, I guess I should have said this at the beginning. I'm assuming that everybody kind of has some sort of familiarity with EMT analyses as part of this. I did include a short primer, if you don't, on what EMT is, what an EMT study actually is in the appendix. So if you don't have much experience, I encourage you to go take a look at that. But back to when we were running EMT studies. So the majority of the EMT study requirement does come from the interconnection process. We made that a requirement starting in 2013. And again, as I mentioned, it spawned from that initial assessment of the instantaneous overvoltages and control parameterization studies that were needed to mitigate those issues. And since then, we've gained a lot of experience with these EMT models. And so it's sort of morphed into understanding that EMT models are really, from our perspective, the best way to look at the high fidelity sort of modeling of these controls and logic that are within inverter-based resources. And so now, fast forward to 2024, any inverter-based resource that's coming into our interconnection queue does require an EMT analysis as part of that system impact study. And so, other reasons that we might be running an EMT study outside of that is, there's studies that come in for reliability upgrades. And so, I've kind of listed here the sort of phenomena that we're looking for in different studies, even just outside of the system impact studies, things like weak system, subsynchronous oscillations, control interactions, ride through, performance verification is kind of a new one. And any other sort of instantaneous voltage transients. In system impact studies specifically, we are looking for more of the weak system conditions and the ride through. We haven't had too much of an issue with the control interactions yet, but the only part of our system that's I would say saturated with IBRs is up in that northern Maine area. So how do we run these EMT studies? So we always start off with our steady state and our stability cases as our baseline, right? That is the sort of ground truth and our initialization point for our EMT studies. So ISO New England uses PSCAD and the ETRAN software together to very quickly create our cases for study purposes. And the intent there is we have a lot of background in developing steady state and stability cases. We have a lot of different assumptions, a lot of different standards and requirements that goes into those models. And so we really didn't see a need to reinvent the wheel in that respect for EMT studies if we can just port everything right over. And so this step really saves us a lot of time. And so, the ETRAN software also allows us to take those dynamic models that we, wouldn't normally ask for, right, from, say, an OEM or a developer and port it right into its sort of equivalent model in EMT space. And so, that's kind of what this diagram is showing, is that, we start off with our PSC case and we convert it into a PSCAD case. Normally, the system is much larger when we're doing system impact studies. We're talking, hundreds of buses, but, that'd be kind of hard to put on a slide here. So, moving forward, the kind of things that we are actually running in, once we have our cases set up is we then put a lot of kind of engineering judgment into what we're going to run on these cases. Interconnection system impact studies require full N-1 and N-1-1 analysis. But the decision on which specific, faults to run is really up to the tech lead and the engineering folks who are running this study. Because, again, when we're talking about EMT models, they are far more complex and far more computationally expensive than your normal sort of positive sequence dynamic models. And so we have to really be choosy about which ones we're running because, if you think about with a stability study, we may have 10 different cases that we're trying to run, and we're trying to run 50 or 60 different, stability simulations on each of those cases, right? So you permute it, you end up with, a lot of different simulations. If we tried to do that in EMT space, the study would never get done, given how long it takes for a single one of these sort of contingency runs to finish. A lot of work also goes into how we're setting up the boundaries in our cases. So again, we're not running the entire Eastern interconnection, for example, in EMT space. We are doing that in stability space and steady state space, but in EMT space, again, it would just take far too long per contingency. And so, what we're looking for in the boundary setup is, how many of the projects can we include that are local and relevant to the project under study? And how much of the transmission, subtransmission, distribution do we need to include as well? Again, to make sure that we're we're not only running the study in an efficient way, but also to make sure that we're getting the results out of it that we want, or that we're looking for. And again, this does result in a large amount of EMT studies. We can end up with hundreds of buses and 50 or 60 specific project models. And so some of these contingency runs, even on really powerful hardware, can take anywhere from 9 to 12 hours. And so, in almost all cases, these sort of studies and cases are being run using parallel processing, because otherwise it would be exorbitantly long. So moving on to the actual models that we're using. As I mentioned, the models come in for the interconnection studies. We do have a requirement for all interconnection requests that come into ISO New England that they provide, again, for inverter-based resources, which if everyone attended the keynote speech from Gordon, I'm sure you saw the queue and how many inverter-based resource requests we have. I think we're up to 46 gigawatts worth of IBRs in the queue, and we're only a 26 gigawatt system. So so it's a lot of EMT models coming in and getting vetted and used in these studies. So when they come in the interconnection request, they're vetted for what we call accuracy, usability, and efficiency. And we have certain requirements for each of these EMT models that cover things, and have them listed here. Things like the model quality attestations, which are attestations from both the developer and the original equipment manufacturer that the EMT model that they're providing us is representative of the physical equipment that the developer is planning on using for their project. We have the model quality checklist, which includes, again, those things I mentioned: accuracy, usability, and efficiency. Again, to make it so these EMT studies don't take, years and years to accomplish. We have benchmarking requirements for benchmarking the EMT model against the RMS model. We do generally believe that the EMT model is a more accurate version, and I'll talk a little bit about the benchmarking later. We have SMIB testing requirements, which is kind of what I'm showing on here is what that SMIB setup might look like, where we have a controllable SCR network, because as part of our requirements, we do require that these different tests for the SMIB testing be run at different strengths of the system. And different faults are run, LVRT, HVRT, angle changes, right? A whole gambit. And we do have all these listed now in our planning procedure 5-6 in Appendix C, C-1, and C-2. So I also recommend folks go and take a look at that, for further information there. Moving another point on the models, something that we're always looking for is how accurate the models are. And so what we want are models that represent the full, detailed inner loop controls of the IBR. And what I'm showing here is a generic representation, but what we're after is a model that accurately represents the equipment, again, from the OEM. And so generally what that means is that they will submit what's called a black box model, which means that we don't get to see all of the innards of it. But we also want that black box model to use what we call it's supposed to be real code model, which means it actually has the code from the field in that black box. We don't always get this, and so there are approximations made when needed. But what we always recommend and what we are always asking for is the highest fidelity, highest accuracy model for each of these. So this is what a benchmark might look like. This one is one that would actually happen during a system impact study. And what we can see is sort of the averaged response of the PSC model versus the PSCAD model. Doesn't really match very well. We see some oscillations here. Folks who are familiar with EMT can probably point out exactly what's going on here. But you can kind of see that the voltage, the profile doesn't really match the reactive output. Sorry, and what we're comparing on the left to the right is the green traces, if that's visible to folks. So yeah, just in general, there's a lot of kind of discrepancy between both PSCAD and PSSE. And, you know, one thing that we're looking for in these benchmarks, we're never looking for an unbalanced type you know, disturbance to match well with a, you know, and say PSSE model, because we know that that's just not going to happen. And we're also not looking for an exact match, even when we're talking about, you know, balance type faults that may be, you know, identical between the two simulation domains. But what we are looking for is a sort of average response to be very similar. And obviously it's always very subjective. But that's why we sort of tend to not get into the weeds of how close is close enough. And you know, what we're looking for is just as long as the approximate overall response matches, that's what we're looking for. And that's what we see here, right? The high frequency oscillations are gone. And again, you know, folks who are familiar can probably see what the mitigation here was, based on the plots on the left. You know, but now we see that the power, right, the ramp time is very similar now, right? You have some extra mode in the PSCAD result, but that you don't see in PSSE. But again, the overall response between PSCAD and PSSE does match pretty well. And same thing in the reactive output and the green plot, right? You see some oscillations in the PSCAD as where you don't in the PSSE. And again, you know, the oscillations here specifically are coming from the addition of a synchronous condenser. But the reason that we don't see them in PSSE is because, again, in PSSE, we have a much larger network. As we're in PSCAD, we've cut the boundaries, right, and put voltage sources at those boundaries. And so you don't always get the same dynamics between them, but again, the overall average response does look very similar. And so this is what we would consider a, you know, an acceptable benchmark between, say, a PSCAD model and an RMS, you know, positive sequence phasor domain model. Some other, you know, model work that we're, I would say, just dipping our toes into is DFR playback for EMT models. You know, what we can see here is that if you look at the top left graph there, the brown is what the model response was. The green is what the real response was. And this was a response for a pretty benign disturbance on the system. There was a substation that was a few substations away from this plant specifically. And there was low SF6 on one of the breakers. And so there was a bus trip at that station. However, at this plant, there was really only a 10% voltage deviation. And it was actually, I think, over the course of like 5 seconds. So it was relatively small and relatively, you know, long duration. But what the plant did was you know, you can see that it reduced very quickly down by 80% of its pre-disturbance output. And so, you know, EMT model verification can be used in kind of multiple ways, right? One, we can compare the actual response to the models, but also two, we can look for specific performance issues as well, you know, with these models, as long as they are accurate. And so, you know, you can see that there's, you know, discrepancy between the real power, between the voltage, the reactive power. And so, you know, we would consider this, you know, this EMT model not to be very accurate. And you know, we're continuing to follow up on this. So some lessons learned about EMT studies, you know, from ISO New England's perspective. EMT studies are much more time intensive than traditional transient stability studies. Again, the models are far more computationally expensive because of how much more complex they are. That complexity does come with higher fidelity and more accuracy, but again, it has to be parameterized and set up correctly to represent the physical equipment for that to be, you know, your end use. EMT studies, you know, again, the reason you always want to run EMT studies here is because EMT studies can show you things that are most likely missing in your stability studies. There are just phenomena that are within, you know, your positive sequence, or sorry, there are phenomena in your EMT or your time domain that just don't exist in your positive sequence phasor domain. And so again, you're running EMT studies for, you know, software-defined devices like inverter-based resources. Again, is very important. Starting studies early and doing them in parallel does help a lot when you're trying to get these interconnection studies done quickly. The EMT studies in our case generally do take the longest out of any part of these system impact studies. And so it does help, again, to kind of keep these things moving forward together. But also don't wait until the last minute, right? Don't wait until you need an EMT study to start, say, collecting EMT models and starting to get familiar with EMT, because it takes a long time to get folks trained up. It takes a long time to collect the models, to get your developers in your region used to submitting those models, to getting them to submit models that meet the requirements. All these sort of, things that, as maybe engineers, we don't always think about, maybe the administrative side of things is generally what takes the longest. And investing in more powerful hardware. You're not going to take your normal office laptop and run a parallel EMT case with 100 buses and 60 different OEM models. It's, like I said, it's going to take a month and a half just to get through it. So, investing in specific hardware and ways to actually run these studies is very important as well. So some ways that we are trying to tackle these lessons learned. We are currently developing an EMT model repository. And what this is meant to be is a single source for all up-to-date EMT models for all projects in New England. So far, we are up to, I think, it's a little over 100 models that we have in our repository. And the intent of the repository, again, is to have each of these models be plug and play. So you'll have sort of a wrapper around each of them that just allows us to put it right into our case, our PSCAD case, and run with it without any sort of initialization concerns. We're also looking into which hardware setups are most beneficial, right? Whether we want to buy in-house hardware or say if we want to run these on the cloud. So right now we're looking at which of those is most beneficial. We're designing some automated testing and verification tools for EMT models. Currently, we have a tool that does it for positive sequence dynamic models called the model acceptance tool, but we want to bridge this over to EMT space as well, so we can use it for things like conformity assessments for IEEE 2800 and playback for validating EMT models. And we're also looking at the viability of hybrid simulations for possibly operational studies as well. And I think I finished right on time, so I'll hand back over to Julia. Thanks.
Right. Thanks so much, Brad. And very impressive. May I ask how many people do you have working on this on any given day with 40 gigawatts coming?
On any given day, it's a lot of people's side jobs. So we probably have, I don't know, 8 folks whose side job it is. We don't have anybody who's like 100% focused on it, but that's kind of where we're going, right? Is we're looking for more folks to kind of fill those sorts of roles. So we do rely on consultants a lot for this work.
All right, thank you. And speaking of consultants, so the next one will be kind of like broader overview about industry uptake and how to make EMT studies more manageable. And this is coming up from Andrew Isaacs, who is Vice President of Electranix.
Hello, everyone. So I got 20 minutes. So we're consultants, like Julia said. We write tools for studies. We do a lot of EMT studies. That's sort of our specialty, and we work for people all over the place. And so I was given this task to write or do a 20-minute talk on making EMT studies more manageable. So that's my job for today. So I'm going to take a little step back from some of the details that Brad presented. I'm going to quickly just remind you all why we're talking about EMT altogether. Okay, so we have, my first bullet says, well, NERC recommends, IEEE recommends, other people are doing it. It's not going anywhere, and probably actually you will be required to do this pretty soon. Okay, so leaving all of that aside, why are we doing it? It's because it's filling a gap in the tools that we have right now. It's answering questions that we can't get the answers to without that specific tool. So the tools we're using outside of EMT are missing things. Okay, we had some examples in the earlier presentations of that, and that's very common with our evolving grid. So the corollary for that is that if you're not doing EMT correctly, you're still missing those things, okay? And you're probably just adding a lot of expense and a lot of time without adding a value from the EMT. So it's always good to keep in our minds that we're trying to answer specific questions. We're trying to add value to our process. We're not just trying to add work and difficulty. So the perception that I want to try and talk about is that EMT adoption is overwhelming. Okay, you look at what, where ISO New England is now. They've got 8 people who are working on it. They're doing every single interconnection is doing a study. They've got all this model processes and databases and everything. How did they get there? Okay, from 10 years ago. So, at risk of talking down to people, but when someone asks me, when they're my daughter, for example, will ask me how, she feels overwhelmed by something or it's unmanageable, we try and break it into pieces, right? So what is a thing that we can work on? And then we can put these things together and solve this problem like that. So I've tried to take this EMT problem and break it down into pieces, okay? So here's the pieces. Under EMT capability, we've got this green bit, and I'm color coding it based on challenge, okay? The green bit is like buying tools and making requirements. It's actually really not that hard to do, right? You can go out and buy software. You can copy a requirement. The orange bit is data collection and organization and system modeling, okay? And you might think that's the hard bit because that's like building the models, right? That's the part that takes a lot of time, but actually I'll put that in the category of, achievable. Very well, they're all achievable, but this is technical, time intensive, but not that hard to do actually. And then we have this third category, which is study needs identification, scoping of studies, and actually doing analysis and making decisions, where I would put this as technically the most difficult thing to do, even if it doesn't take the most time. So let's break it down a little bit more. We'll say that in this easiest part, okay, you can do this part. You can buy tools. There's strong commercial options out there. You can get some advice, talk to other people who are doing this and find out how they do it. Likewise, there's lots of people doing requirements for EMT now. There's lots of good examples. There's templates. So this part you've got, right? That's the beginning. This is something very achievable and doable now. I've got a slide here for your reference of requirements. If you're looking for a place to start with requirements, there's actually very good guidance from NERC now. The IEEE 2800 2022 has a detailed list of EMT modeling requirements. And there's public stuff that we maintain and post for free. You can take it and modify it and use it how you like based on our experience. Okay, so this is something that is also very doable. So going to the next level. So we're going to say this is the easier parts. You can still do this, but now you're going to need to dig in a little bit. So the 2 ways I've broken it down is data collection and organization, and then the system modeling piece. So the data collection, I would say, is the most trainable task. You can get a few days training and be doing this, okay? So you check the models you're getting, you build a simple test bench system, and it takes time, but it can be made quite efficient. You can do it efficiently. Organizing the data is something that you don't have to, out of the gate, be too organized. But over time, as you get to the place where ISO New England is, where you have hundreds of models with many versions of those models over time, you're going to need to be more organized. And this is a data problem, right? An organization problem. You can use databases and so on. And then the next step is to actually put the models together into a composite system model. And this is more advanced, but also trainable. This is something we have very, powerful tools to do. And I want to emphasize this a little bit. You don't have to build system-wide models. Okay. In fact, we don't generally recommend doing that. EMT is a intense simulation process. As Brad said, it's computationally intensive. We want to be as light on our feet as we can. And so we're surgical about how we use it, right? We don't need to just build another MMWG model. we want to be surgical about it. And so we're careful with how we build those models. And I want to really point out that this is all stuff that somebody straight out of college can do. Okay, you can hire somebody, give them a little bit of training, give them some tools, and a young, bright electrical engineer is going to love this. This is really good work for junior engineers. And so you can leverage that part of your organization to do this kind of work. It's very educational, it's very helpful, and they're very good at it because they're good with tools. Okay, if I'm going to generalize wildly. Okay, and then I'll say the easy part you can still do, but now you're going to need to take all of that work that the junior engineers have done and decide how we're going to do this surgery on our system. How are we going to decide what to study and when and why? What questions are we answering, right? And how are we going to solve them once we get those answers? So the analysis requires engineering judgment. And actually the scoping, so the beginning where you're scoping and the end part when you're actually looking at the results are the part where you need those senior engineers. You need strong engineering skills, power systems engineering skills. And this is where you want to call up your senior engineers, okay? Get them in to look at it, maybe 2 hours at the beginning of the study to say, should we be doing this study? Should we change our assumptions or our boundaries? So I want to give you a quick example of what I mean by study need and need identification and scoping. So we have tools like short circuit ratio metrics, all right? Everyone's really interested in using screening analysis for EMT. How do we decide when to do an EMT study? We could choose an SCR level, for example. Let's just say we did that and we said, SCR of 2 is our screening threshold. I'm not recommending you do this, by the way, okay? I'm just saying that's what we've decided to do. So we got 2 systems here. The first system on the left is TSO number 1, we'll call them. They've got a 500 bus network with a peak load of 200 megawatts. And they're connecting a 50 megawatt IBR. And the short circuit ratio at the point of interconnection for the IBR is 2. Okay, so we're going to say that meets our criteria. We should do a study. Now we go over to the study on the right, or the situation on the right. We have a new TSO number 2 with a 10,000 bus system with a 10,000 megawatt peak load. And now we've got 3 plants connecting. 2 very large ones, maybe they're offshore wind plants with SCR2 and SCR 1.5. And then we have the same problem on the left. We have a 50 megawatt IBR connecting with an SCR2. So by our screening metric and by all accounts, does the study in both systems, or does the 50 megawatt IBR in both systems deserve a study? Should it be studied? Yes, we should, right? It's met our criteria. It probably, it's a risk of having a problem. If you've got limited resources, and everybody has limited resources, which one should you study, right? The one on the left, 1 engineer available and 2 months to perform the study. You should study your 50 megawatt IBR. It's really important for you. On the right, you see that you have another wind farm over there that's going to be much more important for you, and you probably don't have time to study the 50 megawatts, so you're going to leave it out. Now, that's not to say you shouldn't study both. EMT will add value for both, but you need somebody who can understand what's most important for your network to be able to make calls like that. Okay, this is a gnarly slide. I'll try and not just erase all the benefit of this simplification presentation by adding a gnarly slide to you, but I'm trying to, if you can remember those color codes, we had the yellow and the orange, where those processes happen. This is an example of how we do a commercial EMT study and how we train other people to do it. So on the left side, all of this stuff are pieces of inputs into an EMT study. And most of it is, again, bite-sized, achievable things, although sometimes a lot of work, like a phasor domain study. You do your PSSE dynamic studies, and that's an input into this process. You're finding out how, it's helping you screen. You get all of your verified IBR models. You've tested them all and benchmarked them like Brad described. You have system component models, transmission lines, and all those things. This is all your junior engineer collecting all and building all these models and building them into potentially a database. This is probably ideal situation for now. We'll say you're not starting here, but All of that counts as this sort of input management of the EMT data that you use. On the bottom, you have a little piece of experienced engineer to do that scoping and studying, and that's defining where your study is eventually going to be done. That's carving out the piece of the system that you need. And then we use these tools, conversion to EMT. Brad discussed ETRAN, that's where that would go. That's system modeling. Basically, it just produces, these tools will just produce the system model in PSCAD. If you want to use parallel and hybrid engines, they tie in. You get your model at the end of the day is just really there to produce results. And then your senior engineer, again, does the analysis. And I want to just emphasize that all of this part here on the right that seems overwhelming is mostly done by tools. Okay, we don't actually do a lot of work. It doesn't take a lot of time to do that part, especially once you've invested a little bit in processes. This stuff on the left is a continual sort of thing that continues to happen. So we're implying here that you need probably a team, you need people. And, you know, this is where I know I'm just going to lose a lot of you, right? Because you're all busy. You don't have dedicated EMT teams. You don't have, you know, extra time in your day job to take on all this stuff. And what I'm telling you is that EMT is coming. You're going to need those people. Okay, you're going to start to invest in people. You're going to need to fund that. You're going to give resources to those people. You need to buy the computers, buy the software, give them time to do that. So there's no real shortcut to that. Okay, you're going to have to get there eventually. I've got an EMT team is ideal, or, you know, individual superhero. I know there are a few of you superheroes out there who are on your own. Hopefully that changes, right? Over time, you're going to need more help. But your team looks like this. You've got hopefully a junior group of engineers. Doesn't have to be junior, but can be, you know, strong computer skills, putting that data together, collecting it, checking it, doing the system modeling. You have your requirements and tools. Your requirements people especially will be your regulatory, you know, your compliance people, whatever you need to do to enforce that. And then you have hopefully a bit of senior engineering experience in the team to make the whole thing useful. Okay. You can decide where you are on this picture. I wanted to give a quick summary, just from a small sample from among our, you know, our industry friends that I took, and the names are missing to protect the innocent. I've got 9 TOs or ISOs on this table, 1 through 9, and you can see along the left various, and you might not be able to read it. Sorry if you can't, I'll read them for you. But your various levels of adoption of EMT, okay, where we're at in these processes. So along the top, we just say collecting an EMT model. Is this group collecting an EMT model? And this is getting much better, okay? And if you're not doing this, you should be, okay? That's step 1, is to be asking for an EMT model, even before you buy the tools, if you need to. But it's very hard to go back and get those models afterwards. So get the models. Second piece, EMT model performance and quality report. So you're not only asking for a model, you're asking for some work to be done on that model. Show us that it works, right? Show us that you pass basic performance tests, that you are, you know, you've got some basic quality going on. And that's also fairly well done right now in the industry. EMT model performance quality tests. This would be now, you get the model, you get the performance check, and you also check it yourself. Okay, you're like, that's good. I'm really grateful that you did that screening work to get the model in here. I'm just gonna, you know, I believe you, but I'm just gonna check it myself as well, right? And make sure that it works. The fourth one is you do some benchmarking, or you're asking for a benchmarking report. You're saying, give us the model, PSCAD, PSSE, or whatever tools you're using, and then show us what they look like against each other. The fifth one would be, again, we believe you, we're just going to also check it, okay? The sixth one is we're asking for a model validation report. And you can see right now, this is done very rarely, or I would say not in a very advanced way. And this is something that is a fundamental sort of suggested change by the IEEE 2800 and 2800.2, There'll be a talk about that in the I2X seminar, this validation piece and the validation report that comes out of there. This is something that's coming for the industry, currently not very well adopted. The next stage we have, an EMT study is done always. So when you get your model, you always do an interconnection study. So, you know, Brad said that ISO New England does that. It would probably, if they were on this chart, they would be one of those ones, right? That would be, you know, fairly advanced level of EMT adoption where you're actually able to do a study every time somebody asks for an interconnection. And then the last two we're just going to say are sort of as needed. So if you're near a series capacitor, or if you've done a screening study and you have some method of choosing when to do a study, or you do a manual review and you do a study in that case, but not every time, that's a realistic scenario for a lot of very large utilities, okay? Now, I just wanted to highlight this one here. One of our friends has this in there. They want to do EMT studies, but they'll only do that. They'll only ask for a model if they feel like they need to do a study. So they don't have this piece up at the top where they always ask for a model. And that, I promise you, that will get you in trouble, okay? So I want to re-emphasize that that's something that needs to happen every time. To finish, I'm just going to give you hopefully a hopeful summary. Each component of this process is manageable. This is something that all utilities can do if you provide some resources, and it can be staged as well. So the first thing you need to do is immediately be implementing requirements for EMT models, and establishing an intake process should be your highest priority, okay, for EMT adoption. That has to, the models, you have to have the models before you do anything. And those models, you don't necessarily get a second chance to get the models. At interconnection time, you can get them. Afterwards, you may or may not be able to get them. And that will poison all of your future studies. If you don't have good models for past stuff, your future studies are going to be having that blot on them, that asterisk always, that you're missing that data. After you've got your models, you have to continue building on that foundation, right? You need to scale it. You need to become more efficient and better at it. You need that expert study need identification. So screening metrics, and honestly, it's senior engineers looking at maps. That's my best advice for screening right now. You need to manage the data that's coming in as you get more of it. You need the fast and accurate study model construction, and that's basically tools and tool expertise, which is, again, achievable. They're not particularly difficult. And they're getting better, by the way. There are also people building new tools, thinking about this problem of automation and study model building. This is coming, right, for the industry. We can see it coming. You want to be able to process those results automatically, to be able to take models in and have tools that will help you screen them, help you review them and analyze them, so that you can apply that last layer of engineering judgment to it from senior engineers. So again, at the end, we say all of this can be done. Some of it can be done quickly and soon, and all of it will require at least some investment in people. So you really need to be looking at helping your teams out by not just adding this onto your one, small group of engineers. You're going to actually resource that team and grow it over time. I think that's all I have to say about that.
Thank you, Andrea. Thank you, Andrea. And last but not least, Brad mentioned that NERC is also looking at, EMT is not going anywhere, and NERC is looking to write some guidelines, write some standards on EMT modeling. So next up is Thant, who is an engineer and inverter-based resource specialist at NERC. And he'll be talking about EMT task force at NERC.
Thank you, Julia. Good afternoon. My name is Aung. I'm a senior engineer from NERC and their engineering and security integration team. I also coordinate EMT task force at NERC. And it's really a group of really passionate people in this modeling space. And it's just a privilege and honor to be working with them. I know there are a few of you here in this room, so hats off to you and thank you very much. Just a quick outline of my presentation today. Quickly go over our strategy, what our mission is, our overview of our current work items, review of our reliability guidelines on EMT modeling and studies, and quick updates on our latest work items and looking ahead to the next year. So our goal is a widespread adoption of EMT modeling 2 in interconnection and planning studies. I do have planning here, but for the moment, we're focusing on interconnection studies. Our approach is 5-pronged to make modeling more accessible and approachable. And I really like Andrew's presentation earlier, breaking down this seemingly large task into a manageable pieces. So some invitations in the future for Andrew to the task force meeting one of these months. And creating a common understanding, right? And promoting the motivation. Why do we need to do this? And decoupling from other processes, right? So there are other processes involved in interconnecting the resource, and there are a lot of dependencies. So what we first set out to do was, okay, let's not bogged down with these too many dependencies, and let's think about what is the ideal requirements, ideal things to do. And then, well, at least we have a reference. And from there, we can start to consider other dependencies. And creating a baseline and unified approach, that's where NERC standards project come in, introducing specific language around having EMT studies in our standards like FACT 2 and MOD standards. A quick review of our work item this year. These are the resources that we hope will set the industry up for success. Number one is our continued support of the EMT modeling standard project team. Work item 2, we have a reliability guideline, recommended practices for performing EMT system studies for IBRs. Third is an online organized repository of curated EMT modeling resources, quote unquote EMT curriculum. It's meant to bring a fresh engineer from the ground up to be comfortable using EMT tools for interconnection studies. The fourth is the white paper. It's looking at the adoption of EMT modeling and the studies in interconnection and planning studies for PBS connected IBRs. As part of that, we have done a survey, and some of the results I'll go over in the next few slides. The last work item is EMT analysis and operations. Again, it's a white paper. In fact, the task is being led by one of the great engineers from ISO New England. So our goals for this year is to publish 3 papers. One is a guideline, that's number 2, and 2 white papers, number 4 and number 5, and go live with the online EMT repository of modeling resources. So just to visualize how we're working with the industry and we're supporting each other in this journey of retooling the industry with the EMT tools. In the dotted box, we have an individual TPs and PC. You can visualize the maturing the EMT experience through stages. As Andrew mentioned earlier, getting the model right now is very important. So that's a stage 1, establish the EMT model requirement. And there's already a template from 2023, last year EMT guideline from NERC, as well as from Electranix and a bunch of other examples. I think technically it's fairly easy because it's already available. I think, and on the process wise, for an entity to adopt a requirement, they may have to go through the stakeholder process, and that's where things get a bit tricky. But nonetheless, we working with NERC and with these guidelines, what providing the individual TPs and PCs to have a strong technical reference and justification, and as well as the regulatory framework to support their push for the model requirement establishment. Stage 2, model quality verification. And I think that is a very important piece from the past 10 years. We have learned the lessons where if we just get the models and don't ever check it, they will collect dust. And when we actually need to use it, they might not even work. They might not even be specific to that site. So that's a very important thing. We need to do at least the first 3 stages, where the third stage is where we're testing in the SMIP single machine Inverter-Based that you saw earlier in Brett's presentation. At least do the first 3 stages, and that's actually the scope of our last year guideline. And then getting into screening and integration of the EMT study processes into the interconnection process, and regularly performing these interconnection studies in EMT. And throughout each of the stages, there will be lessons learned, and hopefully will feed back into EMT model requirements. And the experience from each of the TPs and PCs is where we'll hopefully will be gather and collectively learn at the task force level and share with the rest of the TPs and PCs. So just kind of a different view of this, the first 3 stages. We covered that in we call it the volume 1. The last 2 stages are being covered by the volume 2. That's the guideline that we're working on this year and targeting publication in 2 months. Just to kind of give a quick overview of what we covered already in volume 1. We touched on model quality, model verification, attestation, model. We even provide a sample model checklist which can be used as a requirement. And very important piece is that we started touching on the equipment-specific EMT model validation report, right? So that's already been recommended strongly in our reliability guideline, and also as well as benchmarking to the positive sequence dynamic models in an attempt to also improve the other tools as well. So really, this paper laid the groundwork for what we mean by model quality. We're not going to get into this, just want to give an idea that this crazy flowchart exists in that guideline, and I encourage you to take a look at it. It's been the work of many smart engineers, and yes, it's really established just the EMT model that you're going to get from your requirement will be meaningful and useful, and so that we don't end up wasting time with the low quality models. All right, now I'm going to get into the work item updates. The first one, the work item number 2 is a guideline on the EMT studies. I think I didn't do my math right. It's actually 8 chapters and 4 appendixes. It was out for 45-day industry comment period. It ended in middle of August, and we had about over 200 comments from the industry. I think one of the most common awards will go to ARCOT, and it's with really good comments from them. And if you're in the room, thank you. So yeah, really the purpose of this is for the transmission planning engineers to know when and how to study the impact of IBRs on the BPS in the EMT domain. And the focus is within the gender interconnection study process, primarily system impact studies. And obviously we're not focusing on any conventional EMT study like installation coordinations. So keep an eye out for this. The team has been working hard every week. So I think I'll drop that date is sometime next week. So, all right. So just to kind of help you visualize this work item in a flow chart, which is, you can guess it, inspired by the chart that Andrew showed earlier. It's also because one of the co-lead for this task who's helping with me, he's also from Electranix. Thank you, Electranix. We have all the data input coming into the model building block in the middle. And the big arrows are showing the steps, right? Screening is covered in chapter 1. And we have steady area selections covering chapter 2 of the paper. And the detailed system model component models covering chapter 3. And there's also chapter 5 and chapter 7. They also feed it into They also feed it into the models building process, right? So, and there's a chapter 7 here, although it's later part, but it's actually one of the critical piece, is hardware in the loop validation of IBR models. So we asked about model validation report. So that's what we're looking for, right? We want actual hardware in the loop of testing and compare them with the EMT model and produce a validation report showing benchmarking between the real product response and the model response. And the chapter 5 covers the identify the contingencies, and that all feeds into the model building process. And you'll see that's the accelerated EMT simulations. Chapter 8 is in there. That's really talk about parallelization, multi-rate simulation, multi-rate being multiple time step, and the hybrid simulations as well. So and all of that feeds into the building the model. If you're utilizing the parallelization, you end up with a model that is already built to be parallelized, to be solved over different cores or different computers, or it could just be one core solution. But at the end of the day, you have a model, and we want to benchmark that model against the original input sources, right? So if we came from a positive sequence phasor domain, so at least within the bandwidth of the accuracy, we want to be able to go back and make sure that, okay, we have the right load flow, we have the right dispatch. And once we've done that, then we go into the chapter 6, that's actually performing the studies. Here we have, this is where we have automation comes in, not only to automate the simulation for different contingencies, but also to process the results. The next work item is work item 4. It's a case study EMT modeling adoption. We send out a 46-question survey to every single TPs and PCs. And we posted it on a compliant bulletin. Over 40 organizations participated. I think that's, we have about 200 TPs and PCs, so about 20%, not bad. And if you're from the organization that participated, thank you. So just to kind of go over some of the survey results that's easy to show, we have other results that require typing in a response, but these are easy yes or no ones. Are you aware of the NERC guideline on the EMT model requirement? We have over 90% yes. That's great. Are you aware of the NERC EMT standard authorization request or the standard project? Close to 90%. That's really good. Do you require submission of unit model validation report, which compares EMT model to either lab or HIL, how in the loop test of actual inverter unit? So here we have about 75% no. I think this area is where we want to improve in the industry on working together. And do you plan to develop EMT model for the entire system within the organization? We have about a third of the correspondents having that aspirations. About close to 70% are not looking at that. And then, as Andrew said, you might not be needed, right? There are multiple approaches. Are you running EMT transient hybrid simulation? The core simulation with the phasor software. About 90% is not yet doing it. Are they replicating system events with EMT model? Only a third is doing that right now. Hopefully we can see this number increase in the next 3 to 4 years. Do you require GOB's report when changes happen in the field, such as firmware upgrades? So we have about 60% saying yes. Again, we want to see that increasing. This doesn't really have much to do with the modeling part, but this has to do with how we can keep the model continuously updated. This feeds into the next work item, the EMT analysis operations. Do you leverage plan to rely on parallel processing for improved steady efficiency? Good to see that 75% are already thinking about it. Oops, sorry. Work item 3 is EMT repo. There's a temporary home thanks to BNNL. We hosted it on the GitHub. It's open to public. It's there is issue reporting and tracking. Public can access, request new items. There's also change management built in. We're trying to set up the permanent home for this. I think we're gonna go with this with Microsoft solutions instead of the GitHub solutions. They're currently under constructions, but this is what we want. What we expect to go live end of the year. Working through some cybersecurity concerns right now. this new item under that work item is the EMT model portability white paper. Everyone is invited to go and review and provide feedback. And next revision of that work item, that particular white paper is to incorporate the IEEE C-grade power system DLL model standard into this common information model. All right, another flowchart, yeah. So this work item 5 is the EMT analysis and operations. It's very similar to the chart that we see. Obviously, it's developed by slightly different teams or different flavor, but you can kind of see from the top, it's starting from the system impact study, coming into commissioning study, and it takes into account of as spreadsheet model versus as build model. But so this is where we're looking at, if you were to do EMT studies in operation time horizon, where you have really time crunch, how would you do it efficiently? So from our perspective, if you can solve this, you can solve the interconnection problem too. Meaning being able to efficiently do EMT studies in the interconnection process, because you don't have much time to do these kind of studies in operation space. So once all that is laid out, such as the model repository that Brad mentioned earlier, having a vetted model, verified model that's continually updated if there's any changes in the field, and allows the study engineer to pull in sort of off the shelf, ready to go, and perform a study. So please keep an eye out for that as well. And this is also one of the papers that we're trying to push at the end of the year. Looking ahead to 2025, EMT modeling and requirements is going to continue to evolve. We'll need to make revisions to the guideline that we published last year. And I think, we think that it should be a living document. We need to help equip vendors and developers with up-to-date guidance to meet those new requirements. And continue to drive harmonization and consistency across the industry, right? Therefore, increasing the efficiency for everyone. And as industry experience grows, the lessons learned need to be captured and shared broadly. As reference back to the first slide where we had the feedback loop. So we have to continue to do that to foster and maintain that feedback loop for the industry benefits. As the adoption grows, we can expect more strain on the already constrained resources. Andrew mentioned, right, growing a team. Also keep in mind, sometimes it can be a revolving door. So you may be in a situation where you have to continuously be training the folks. So it's always good to have a pipeline coming in and a continuous training process. Continue to support the project, EMT modeling project that's going to go into next year. And we may involve into a working group. Right now it's a task force, which usually have time span of 2 years. Normally it's meant to address just specific risk. But because how we see things evolving, we may evolve into a working group next year. Also, just looking ahead to 2025, the September meeting, we did a poll. Over 50 people was attending the meeting, about half participating in the poll. You can see the size, based on the poll we previously conducted in the beginning of the year, and we did it, and based on new information, so we had these 7 questions, and this is how it ranked. So we may be picking the last, the top 3 or 4 for the next year. So really, I think one of the top one is the model benchmarking example. So in our guideline, we talk about benchmark, EMT, and positive sequence model. And, people want to see what it looks like. Good example, better examples. I think it'll be tricky to come up with a specific criteria like percent, like, within 5%, 10%, that type of language, but we'll see what we can do in the time frame. And the other one is the unit model validation. We talk about requiring it, but what does it look like? And the continued push for the real-time EMT model. Real code EMT model that's based on the real code and using the IEEE C-grade DLL interface standard. All right, get involved, and the task force meets monthly and every 4th Tuesday between 11 and 12:30 p.m. Pacific. That's our website, and it's my email. Thank you.